Unit 3, motion graph. Do not make any calculations for A to D here, okay? It says. So just by looking at this, justify your answer based on the slope information. All right? So what time interval or intervals is the object moving forward? Well, it looks like when object's moving forward, it's going to have a positive slope. And this looks like positive slope, and this looks like positive slope. So from time, t is equal to, let's say 0 to 1 second is definitely a moving forward, right? And t is equal to 2 to 5 seconds is also moving forward as well, right? For part B, what time interval or intervals is the object moving backwards? There's only one time, and that's 5 to 6, okay? So when t is equal to 5 to 6 seconds is when it's moving backwards. And then for part C, what time or time intervals is the object at rest, right? And where is it? Well, it looks like when time t is equal to 1 to 2 seconds, it hasn't changed this position at all, right? So when t is equal to 1 to 2 seconds, right? Objects at rest, and it is x is equal to 10 meters is where it's located, right? So you have to have that as well, right? Then part D, what time interval is the object moving the fastest? It looks like the steepest slope will give you the fastest, right? So the steepest therefore, whether it's positive or negative, it doesn't matter, right? Because they want to know how just fast it is going. So D to E is the steepest slope, right? Because when t is equal to 5 to 6 seconds is the steepest slope, therefore that's when it's going the fastest. And it's going backwards. Okay? Gesundheit. Then for part E, it asks, what is the total distance the object traveled? Well, it looks like it starts at 0, then it travels, right, all the way 10, stays at 10, goes to 40, and then comes all the way back to 0, so now it moved back 40, so total distance traveled looks like, right, so 80 meters. So 10 plus 0 plus 30 plus 40 gives you 80 meters, right? And that's the total distance. So that was easy. Then for F, what was the total displacement? Total displacement means change in position, right? So total displacement is equal to change in position. That means, right, x at 6 minus x at 0, right? The 6 second is the total time. Therefore, 0 minus 0 is equal to 0 meters. X hat is basically the total change in position. It hasn't changed at all, basically. Okay? Alrighty. Was that okay? Was that easy enough? Right? Alright. Let's take a look at the next page. Using the velocity versus time graph below. So again, this is velocity versus time. So you got to be careful here, right? You got to know what you have first. Graph that goes with it, right? Generate the position versus time graph that goes with it. So what do we have to find when we go from velocity versus time graph to position versus time? What's the key word? Begins with A. Area. We have to find the area. So we really should recognize where the time axis is. That's very important. You really need to know where the time axis is, because that's the border for all the areas. Okay? So first is this area here, and this area is below the time axis, and the area for this is simply 1/2 base times height, which is -10 times -10 times 0.5, which is 5, and half of that will be -2.5, right? So -2.5. Then on this side we have +2.5, right? And then on this here box, this is 10 times 0.5, which is simply +5. And then this here is +2.5. And then here looks like -5, because 0.5 times 20 is -10, and half of that is -5. Then we have this, which is -10, and then we have this, which is -10, and then we have this, which is -10. So are we okay with that so far? Yeah? So it says here, well, it looks like I better start at -5 meters when t is equal to 0, and this is very, very important. Okay? So they give us the starting position. If they don't give us the starting position, we can start at 0. But since they give us the starting position, which is when t is equal to 0 seconds, it starts at -5. Then, in half a second, we go to -2.5 meters. So we end up at -7.5. Right? So this here, and it goes to 0 here, so my velocity is approaching 0, therefore I should flatten out. Right? So I should flatten out here. So I should do one of these drones. And then from 0.5 to 1 second, now I'm going in the positive direction, 2.5. So here from -7.5, now I end up at back to -0.5. And I do one of that. Then from here I go 5 meters in the positive direction. So from -5 I go 5 meters in the positive, so I end up at 0. And this one should be a straight line because it is a constant velocity. Right, so straight line, like so, linear graph. Then I go more positive, 2.5, so I end up at here at 2.5 meters from 0, and I flatten out again, so I do one of these. Then from here I go into negative direction 5 meters, so I should end up at -2.5. Okay, -2.5. And then -10, right? -10 and -10. And this should be a straight line because it is a constant velocity. Boom. So this is what it should look like. For the position versus time graph. Are we good? Yeah? Alright. Then, now let's take a look at the next page. Is asking here, use the graph from question 2 to answer the question below. So for particle from 0 to 0.5 seconds, which way is it going? Well, it looks like we have negative values for my velocity. Every time I have negative value, whether it's constant or not constant, slowing down or speeding up, it's going backwards. There's no negotiation on that, right? It's going backwards. What about part? Is it slowing down or is it going constant speed or speeding up? It's definitely slowing down because I start with negative 10 meters per second and I'm approaching 0 meters per second. So I'm definitely slowing down to 0. So it's definitely slowing down. Now from 0.5 to 1.0 seconds, now we're moving forward in the positive direction because it is actually speeding up going in the positive direction because my velocity values are all positive. So it's definitely going forward and it is definitely speeding up. And then it asks, calculate the acceleration value, just the magnitude wise, okay, just magnitude wise, from 2.0 to 2.5 seconds. So my acceleration is equal to simply delta V over delta T, which means since they want, so this is the initial and this is the final. So V at 2.5 seconds minus V at 2.0 seconds over T at 2.5 minus T at 2.0. So the V at 2.5 seconds is right here, and that looks like negative 20, right? So negative 20 meters per second minus V at 2.0. V at 2.0 seconds looks like it's 0 meters per second. And then divide that by 2.5 seconds minus 2.0 seconds. Therefore, this is negative 20 meters per second over 0.5 seconds, or negative 40 meters per second squared, x hat. But since they just want the magnitude, you could say my acceleration is 40 meters per second squared. Is fine. But this is the proper acceleration, okay? Since they want just the magnitude means just the numerical value, so this is good. But if you gave me this, I probably won't mark you wrong, okay? But that's what the magnitude means. This is the actual correct answer, okay? All right, next. Calculate the total distance the particle travels during the time from t is equal to 0 to, oh, what is this? I forgot this. Part D. Part D. Is the acceleration positive or negative direction? I think we already answered that right there. Right? Because it is going in the negative direction. Because the slope value is negative. Right? And it is speeding up in the negative direction. So that's what it is. All right. So how do we calculate the total distance traveled? Total distance traveled is adding up all the change in positions in absolute value. So the first one is 2.5, right? Plus 2.5. So all I'm doing is I'm just adding up all these. I'm just adding up all these in absolute value. Okay? So 2.5 plus 2.5 plus 5 plus 2.5 plus 5 plus 10 plus 10 plus 10. That's what it is. That's the total distance traveled. And hopefully if you use your calculator, your total distance, right, comes out to 47.5 meters. That's the total distance. And then for part F, calculate the displacement of the particle during 0 to 4 seconds. Right? 0 to 4 seconds. So you can do this by saying, okay, well, change in position from 0 to 4 seconds is equal to, right, x at 4 minus x at 0, right? Therefore, what's my x at 4 seconds? My x at 4 seconds is negative 32.5, right? So that's negative 32.5 minus, right, minus x at 0. X at 0 seconds is negative 5. Therefore, it looks like negative 27.5 meters x hat is the change in position or the displacement between 0 to 4 seconds. Are we good? These numbers? X at 4 seconds. I look at this graph right here. This is the position graph. So at 4 seconds, I look at this value and I say, it looks like negative 32.5. Okay? And then X at 0 seconds, 0 seconds right here, looks like negative 5. Is that good? Any other questions? All right, last page. All Now notice it should not take you more than 20 minutes to do this. Okay. Alright, so here we go. Here we go. Ready? A. Calculate the average velocity of an object during the time intervals from 0.0 seconds to 1.5 seconds. So from 0 seconds to 1.5 seconds. So you want to find the average velocity for position versus time graph. So this is the position versus time, right? So how do you find average velocity? You look for the slope of the secant line, right? Slope of secant line. Therefore, you do this. Then you do V average is equal to, right, V at 1.5 minus, I'm sorry, not V, X at 1.5, sorry, minus X at 0 seconds over T at 1.5 minus T at 0. So this one looks like, I don't know, -2, right? That looks like -2. So -2 minus 0 over 1.5 minus 0. So what is that equal to? -2 over 1.5. So what is that? So it looks like -1.33 meters per second as your x hat, as your average velocity. Then for part B, calculate the instantaneous velocity when t is equal to 1 second. So instantaneous velocity will be right here, and you need to draw a tangent line to that. Okay? Again, if you drew your tangent line slightly off, as long as you give me the correct work, I'll give you the full benefit of the doubt. So instantaneous velocity means the slope of tangent line. Right? Then pick 2 points. Pick 2 points. I mean, I can pick probably like these 2 points right here. I could actually pick this point. This looks like it's close to the grid. All right. I could pick those 2 points. All right. So here, V instantaneous is equal to, it looks like I can do X at 1.0 minus X at 0.5 over T at 1.0 minus T at 0.5. So X at 1.0 seconds, it looks like, I don't know, 9.5, almost 10, right? So I'm just going to make it 9.5 minus here, that looks a little less than 20. I'm going to say 19, right? 19, and divide that by, right, 1.0 minus 0.5. So what is, right, 9.5 minus 19? I get negative 9.5 over 0.5. And I get negative 19 meters per second x hat. Now, if you did not come, if you came close to this, if you get like negative 20 or 21, negative 21 or negative 18, I'll give you benefit of the doubt as long as you show me your work. Okay? As long as you show me your work, how you got your 2 points here, and I'll give you the full credit. Then what about C? Indicate all the times when the object is at rest and justify your answer. So when is the object at rest? Well, it looks like whenever there's like flat. So here, this looks pretty flat right here. And so is this right here. This is flat. This is flat. This looks a little flat right here. Right? So these 3 times will be instantaneous velocity at those times will be 0, right? So here looks like 0.6 maybe, right? When t is equal to 0.6 seconds. And here's like when t is equal to 2.5 seconds, right? And t is equal to like 3.8 seconds, right? Right? So you could say to justify your answer, the slope of the tangent lines are 0, right, is good enough justification for me. And I even drew it in right there, so okay. So what you're, for those of you who are taking calculus, what you're really doing is you're basically finding the local maximum and local minimum, right? So when you take a derivative and you set it equal to 0, and you'll get those times. Those times are basically where velocity is 0. All right, what about part D? Part D asks, indicate all times when particles moving with nearly constant velocities. Wow. Nearly constant velocities. Well, that's kind of subjective, I think, but if I were to use my ruler, I don't know, maybe from like 0 to 0.2, right? So when t is equal to 0 to 0.2 seconds, and then maybe here, like, maybe here. So from here to here, all right? So here it's like 1.25 to, I don't know, 1.7, right? So when t is equal to 1.25 seconds to 1.7 seconds, okay? God bless you. And then, I don't know, this is just really cutting it, like, so I'm going to say, like here to maybe, and this is just like really just nitpicking, but I could say like nearly constant at these 2 locations as well, right? So at like when t is equal to 3.2 to 3.35 or something. So those are really nitpicking, okay? And right, the slope looks constant at those time intervals. this means straight line. And last but not least, indicate the object when the object is maximum velocity. Maximum velocity looks like the steepest, and I'm going to say the steepest is from 0 to, when t is equal to 0 to 0.2 looks the steepest. Alright, is that good? Alright, I will stop there for today. Now what happened was